Hi everyone, this video is the solution to example 3 on the topic of plastic beam analysis. In this particular example, we don't have a load of W anymore, so we have real loads of 60 and then a UDL of 10 kilonewton per meter. And now what this question asks is what is the value of the moment, the plastic moment of the section that we need to put in this section so it resists these loads. This is a very similar problem to before, but at the end it has a little detail that we have to address. So let's first talk about collapse mechanisms. In this particular case, we're going to consider two of them. The first one is a collapse mechanism in span AB. So it will occur only in span AB, and we'll have a plastic hinge at A, a plastic hinge underneath the load 60, and then a plastic hinge at B. What we're trying to assume here is that the collapse will be concentrated in bar AB. Another collapse mechanism is one in BC, that we're going to assume that at B we have a plastic hinge, and then we have a plastic hinge in the mid-span of BC, and then you could think about another plastic hinge at C, but if you think about it, point C already allows rotations, so we don't need this plastic hinge here. So I'm just going to write down, because point C already allows rotations, that's technically already a hinge, so you don't need to break the beam for this mechanism to occur. So let's calculate these two. The first one will look like this, and here we have our load of 60, and similar to before, we're going to assume a rotation theta on one of the sides, which then means if that is 2 meters here, that means this displacement here is going to be 2 theta, and then this will close there, and we'll have our plastic hinge here. So if that's theta and the displacement is 2 theta, that means this angle here has to be bigger, will also be 2 theta, and these two angles already are determined. This is theta and this is 2 theta. Similar to before, to have the collapse mechanism occurring and to have the plastic hinges, we need these MPLs to be there, and now we can start calculating our structure. So the first thing we're going to do is the load times the displacement, so that's 60 times 2 theta. This is going to be equal to, and now let's count all our MP theta. So we have 1 here, 2 there, then 3, 4, 5, 6. So we have 6 MP theta. So I'm doing a little bit faster, but I'll count it again. This is 1 here, this is another one, 2. This one counts as 2, so it's 4, and this one also counts as 2, so it's 6. Similar to before, the thetas will simplify, and now what we know is that MP will be equal to 120 divided by 6, so that's 20 kilonewton meter. So now, what is different in this problem when compared to the previous one? In the previous one, we were calculating W, so we were calculating the load that the beam can resist until it collapses. While in this case, we're calculating the plastic moment of the section that we need to prevent this collapse mechanism. So it's a similar thing, but there's a little caveat at the end when we choose which one is critical. So now let's calculate the second mechanism. And here you have to remember that you're not going to need the hinge at the left side because it's already a hinge. So we're going to assume hinge there and a hinge in the middle of the UDL. So in this case, this is going to look like this, then that. And I think this is symmetric. So if this is 4 meters and we're going to assume the hinge to be in the middle, that means it's after 2 meters. So that means this one is theta, this one will also be theta, and all of this will be theta because this is right in the middle. The displacement here is 2 theta. Now, the way you deal with a UDL of 10 or any UDL in this particular case, you have to split it at the hinge. So what we're going to do is we're going to assume that instead of having one UDL of 10, we have 2 UDLs acting at each half on its own. Now, if that is the case, we know that this load here in the middle will be 10 times 2, will just be 20 kilonewton. And this one that represents the other half of the UDL is also 20. And to make sure this works, we're going to also get the displacements underneath these loads of 20, which in this case is theta and theta. And that's how you deal with the UDL. The reason why you have to break the UDL is because this displacement here in the center does not represent the average of the displacement here. So this red function, if you prefer calling it like this. So you have to break it down. So this actually is not important, this 2 theta. And what's important is this one and this one, because these displacements of theta do represent the average of their own function. Okay? So if you use the 2 theta in the middle and multiply by 40, this doesn't work. You have to split the UDL at the hinge, and then everything will work out. So now let's do it, the solution. So we have 20 times theta on the left side plus 20 times theta on the right side. And I forgot to draw my MP, so I have an MP here. I have 2 more MPs here. And now on the right side, remember, I don't have this hinge here, so I don't need any MP to be there. So this is not going to count for our equation. So on the left side, I have MPL times theta, and then I have 2 more MPLs times theta, so I'm going to multiply by 3, and this should give me the right answer. Similar to before, the thetas simplify, and now we're going to get that 3 MPL needs to be equal to 40, and that means MPL is equal to 13.3 kilonewton meter. Okay, so again, what did we find out in this case? We found out that for this collapse mechanism not to occur, we need at least a section that can resist a moment of 13.3. And now, how do we interpret this data? How do we interpret these 2 pieces of information? Which one is critical? Let's read it carefully again. The first moment of 20 says that we need a section that has a resistance of 20 for collapse mechanism 1 not to occur. And the second one, 13.3, says the same thing. So we need a section of 13.3 to make sure the collapse mechanism 2 does not occur. So in this particular case, the critical one is the first one. Because if we want this bar not to collapse, we need an MPL of 20 to make sure it resists both collapse mechanisms, okay? If you go back into the previous video, we chose the smallest load to be critical. And now that we're talking about sections and MPLs, we're actually going to choose the biggest one, okay? The way you wrap around this in your head is there's 2 types of problems that you need to consider. The first type of problem is a capacity problem. That's the one we solved in example 1 and 2. And in the capacity, we know the beam, and we need to find the load, okay? And this load is the capacity that the beam can resist. Now, the problem that we just solved is not a capacity problem because we don't know the beam. We already know the load. And in this type of problems, we call it a design problem. And in this case, we know the load, and what we're trying to do is design the beam and find the beam that resists that load, okay? So at the end of these problems, pay attention to what is the question asking. So when you see some loads, that means you're talking about a design problem. And when you see an unknown in the loads, let's say a W or a lambda, that means we're talking about a capacity problem and you need to find the value of those loads. So I hope this made some sense. We have another problem to go. Thank you for watching this video and have a nice day.